For the first talk of today, we're going to visualize electromagnetic radiation in the range of the Wi-Fi frequencies. We have Friedman Reinhardt from the Munich Technical Institute. He has this junior research project, and with one of his students, he pursued this project. The student is Philip Hall, and the stage is yours. Thanks.
Well, so good morning, and thanks for having me here on this Congress, which I enjoyed very much so far. So in the talk that I would like to give, I would like to look at wireless signals from a very different perspective. When we think of wireless signals, we usually think of data packets, messages, runtimes, protocols, and so on. But we can look at them from a very different point of view, from the point of view that it's actually just light. This is kind of a bold statement, but it's actually a fairly exact statement. So from a physicist's perspective, a wireless signal is virtually the same as the beam of a laser or the light coming from the sun. It's electromagnetic radiation, which is described by Maxwell's equations and so on. So it's an oscillating electric and magnetic field. The only difference to visible light that we can see with our eyes is that the wavelength of these signals is much longer. So while the visible light that makes up the visible world has a wavelength in the range of a micrometer, the wireless signals that we typically employ in our devices have a wavelength in the range of few centimeters to a few tens of centimeters. And as a second very important difference, we cannot see them. So, but from a physicist's perspective, this is very interesting, because that has a somewhat surprising implication. It has the implication that our modern world is actually brightly lit by all the wireless devices that we use every day. So this whole room, as we sit here, it's actually glowing in various colors, only we can't see it because it's glowing somewhere in the microwave radio domain. And this also implies that there is kind of a potential big security leak associated with these wireless devices, in the sense that any device that you use, no matter how well you encrypt your data, is going to transmit a full three-dimensional picture of the world to your environment, no matter what you do. And so when we realized that, we got intrigued, and we wondered whether there would be a way to actually record that radiation and to reveal that picture, to, in a way, build a camera that would be sensitive to this kind of radiation, and that would enable us to see the world in the way that we would see it if our eyes were sensitive in this frequency domain. And so, to cut a long story short, we managed to do that, and this is the result that we got. This is a picture of our lab, and the colorful thing that you see is wireless radiation coming from a router on the backside of the room that we visualize with our method, and we can actually see it propagate in space, and we can even see that objects that we place in the lab cast a shadow in that beam. And in what follows, I would like to walk you through how we did that, and what it might be used for, and I also would like to discuss whether it's actually a serious security concern. But before I do that, I would like to start from a somewhat broader overview and tell you a bit more about what has happened in the past few years in this field. So it turns out that hacking wireless signals, in the sense that in the sense of thinking about other ways, other useful data that we can extract from that signals that are omnipresent in our modern world, it has become quite a vibrant area of research in the past 5 years. And we haven't been the only ones that realized that this is actually a very interesting thing to look at. So there have been many other labs that have pursued many different directions to look at Wi-Fi radiation from a different point of view. And maybe the most famous result is this. This is a result from a group at MIT in Boston, Massachusetts. And they actually hack Wi-Fi routers in the way that they exploit the fact that modern routers have an array of antennas, and they use that to actually send beams in different directions and to focus the beams on the devices that they want to interact with. So modern routers, they can actually send 2 different signals to cell phones on the right and on the left end of the room. And you can hack that. You can use that to scan a beam in 2 dimensions and look at the reflections. So in a way to build a phased array radar, if you wish. And this is the kind of picture that you get with that. So you can scan a beam through the room, you can look at the reflections, and you get a fairly detailed picture of the world. You can even vaguely resolve human beings. You can also just pursue a simpler approach. You can only map attenuation. So you take a Wi-Fi router and a Wi-Fi receiver, and you map the attenuation of the signal between the 2 of them. And you can then mount them on a movable platform. So as a fancy example, for instance, a drone. So you can fly these 2 emitter and receiver drones around a building, map the attenuation on every line of sight that you covered during that flight, do tomography on that data, and by doing that, you can actually extract 3-dimensional views of what has been in between these drones. So there has been a lot of activity in that field, but still this previous work did not yet fully answer this question that we got interested in, like what would the world look with Wi-Fi eyes? And if you look at that question, the state of the art had been pretty much that we had something like the compound eye of an insect. There have been many ways to tamper with wireless radiations in the sense that we look at different directions, either by directing a beam into some direction or by looking at attenuation in a certain direction, and do that for multiple angles to get a coarse picture of the world. And so we got interested in whether we could actually get a full 3-dimensional view of the full wavefront and all the light propagating in space, pretty much in the same way as we can do it with visible light. So we thought about that, and it turned out that you can do it, and you can do it in a surprisingly simple way. So there is a technique that essentially solves this problem, and it's holography. So holograms is something that you probably all have seen. It's these amazing pictures that appear 3-dimensional if you look at them, and that you can tilt, and you can actually look at objects from different angles. They do not look like a photograph. They look much more like a window into a virtual world that has been frozen by taking this hologram. And you can make them actually in a fairly simple way. So you don't even need a lens. All you need to do to record such a hologram is illuminate your object with what we call coherent light. I'll get to that in a second. And record it on a phase-sensitive camera. So these are very technical terms. Let me try to explain that in a more visual way. So in a way, a hologram is a photograph 2.0. It captures more information than a 2-dimensional photograph, which we usually take, where information is restricted in the sense that a usual photograph only captures intensity of light. So it can record in a two-dimensional plane where there was much light and where there was very little light, and the resulting photo will be very bright and very dark, but it's going to be restricted to a two-dimensional plane. It will appear as a flat piece of paper if you look at it. A hologram can do more. So a hologram is a phase-coherent recording, and that in a visual way means that it not only records brightness of the light, it also records the direction of the light beams hitting this hologram during exposure. So in a hologram, in a way, you freeze all the light rays that enter this specific plane, and if you develop that hologram, you, in a way, revive all these light beams again. And so when we look at the hologram, we really look at the very same light rays, at the very same light field that came from the object during exposure. And that in particular implies that we can look at it from various angles and we can have a three-dimensional view of it. So how is that done? So this is done by a phase-coherent recording. And that is this technical term essentially captures this idea of recording direction along with intensity. And to see how that works, I have to, get back to the point that light actually is electromagnetic waves. And waves, pretty much like waves on a lake, have valleys and hills. So areas where electric field is very strong and areas where electric field is very weak. And these valleys and peaks propagate in space. So if you throw a stone into a lake and you watch the resulting waves, you will notice that these waves always move perpendicular to both the peaks and the valleys. So the direction of the wave is in a way encoded in the difference between these peaks and valleys. So if you can take a photograph where you also register whether the peak came first or the valley came first, you also register direction. And that's what it takes. So it takes a light source where these peaks and valleys are very well defined. This is what we call a coherent light source. And it takes a phase-sensitive camera, a camera that can record whether the peaks or the valley came first. Now it turns out that this is a fairly difficult thing to do in the optical domain. People managed to do it, but it was such a big breakthrough that it actually got awarded a Nobel Prize 40 years ago. Fortunately, it's actually much simpler in the radio frequency domain, because the frequency here is much lower than for visible light, and so we can actually record every peak and every valley simply by registering the wave with a good oscilloscope. And that in particular means that it should be possible to do holography of this wireless radiation. So to come up with an experimental setup where we take a picture in some two-dimensional plane of space, we register the brightness and phase of the microwave light at every point in space, and we can then later on use that to reconstruct a virtual view of the world. And this is pretty much how we did it. So this is our experimental setup. We explicitly wanted to capture light from arbitrary devices. So the light sources that we used always were commercial, off-the-shelf Wi-Fi routers that we asked to download a big video from YouTube to generate a lot of traffic and data that we could image. But we make no assumption whatsoever on the signal that they actually emit. It could be anything. It could even be encrypted. We sometimes place some objects in the beam to get a more interesting picture. And we finally record this beam of microwave light in a scanning aperture approach. So unfortunately, it's very expensive to build microwave cameras. You would need a huge array of antennas. So in a first step, it's easier to just take one antenna and scan it across every pixel that you want to image. This is what we did. So we have an antenna that we mounted on a scanning platform, and we referenced that signal to the signal of a stationary antenna. This is what it looked like in real life. So it's, you see, it's not very fancy. It's actually, it's probably the cheapest experiment I've ever been involved in. And so we used plywood and Fischer Technik and tools like that to do it, essentially to solve this problem of scanning the antenna through our lab. But at some point we made it work quite well, and so we could record these pictures. So the signal that we get from this setup is a wave that we can record with an oscilloscope, and that we actually record twice. Once coming from the scanning antenna, this is what is going to make up the image data later on, and once from this reference antenna. So we make no assumption whatsoever on the signal that is transmitted, so we cannot rely on knowing what kind of bits and bytes are transmitted here. But it turns out that if you Fourier transform these signals and you divide them by each other, you can, in a way, normalize that signal to that reference and get a virtual second wave where the bit pattern actually cancels, and you only record the phase delay and the attenuation of that wave as it travels to the scanning antenna. So for every pixel, we record a set of data like on the upper left. We do some processing to remove the bit pattern and only get the coherent wave. And then we end up with something on the lower part of this plot. So we do that for every pixel. For every pixel, we get the brightness, the amplitude, and the phase, the direction of the beam. We actually get that for a wide range of frequencies because Wi Fi is a multi-frequency scheme, so you can have different channels. And we end up with a data set like below. So this is a hologram. It's unfortunately not something that you would easily be able to make sense of just by looking at it. Since we don't have eyes for this radiation, we cannot see the radiation by itself, and even if we record it like that, the information is not very meaningful. But fortunately, there exists a number of reconstruction algorithms. So this problem has been solved in coherent optics, where people actually can render three-dimensional views of what a hologram would look like simply by knowing the pattern that you produce on a photographic plate. So by scanning a photographic plate and feeding that in the right algorithm, you can get a three-dimensional view of the hologram without ever looking at it in real light. And this you can also do with microwave radiation. So from that hologram, we can reconstruct three-dimensional views. We did that, and this is the test setup that in the end worked best. So we have a commercial Wi-Fi router sitting on the back of the lab. It's labeled emitter in the upper picture. We place some absorbing objects in the beam that we made from, aluminum tinfoil. And then we record a hologram in a plane that you cannot see here, that is essentially the front plane of that image. We feed the data into a reconstruction algorithm, and in that way, we can now render a three-dimensional view as it would appear if we had eyes for Wi-Fi radiation and we looked through that plane of the above picture. So we can actually, since it's a three-dimensional approach, we can actually not only reconstruct this view, we can actually focus on different planes. And so this is what we do here. So obviously, a first interesting thing to do is to focus back into the emitter plane. If you focus into the plane of the Wi-Fi router, you actually nicely see a bright spot at one point in the image which is the image of this glowing light bulb in the microwave domain. It turns out, interestingly, that the picture is not very pretty if you just do it like that, because if you only do it with one frequency, with one wavelength of light, you become very sensitive to something that is known as speckles. So this microwave light bounces back and forth between all the walls in the lab, and these waves interfere with each other in a very erratic way, so we end up with something that looks like clouds. And we can, interestingly, enhance that quite a bit if we repeat the experiment for different frequencies, so for different frequency bands within a Wi-Fi channel, and we superimpose the images, we get a much clearer picture where it is very clear that the router is the brightest spot. This is actually something that is very difficult to do with real light. People struggle to make that work. For microwave light, it's essentially straightforward. And we can then go on and focus in different planes. So for instance, in the plane of this absorbing object in the beam. And if we do that, we nicely see that this, so as we move from the emitter to the object, we nicely see how the beam expands, and that once we get to the object plane, there is a big shadow appearing in the light wave. Nicely, you can actually see that if you focus slightly below or slightly above that plane, the image blurs. So it really is a three-dimensional image. It's like focusing with a photo camera. You can blur it if you defocus into the wrong plane. So that's essentially the data that we took. There is potential for a lot more data processing. So it turns out that there are numerous very powerful imaging schemes that work with coherent visible light. So in coherent visible light, you can take just plain dumb photographs as we do that most of the time, but you can also play clever tricks to enhance, for instance, absorbing objects in the light. It's called dark field microscopy. You usually do it with microscopy. You can image polarization of light, or you could enhance only weakly refractive objects. And all these schemes we could actually emulate by just numerically post-processing the hologram data. So there's a lot of things to be looked at, like what does the world look like if we enhance absorbing objects, or do chairs have an index of refraction that is different from air, and questions like that. So in a way to summarize that, we managed to record pictures, and we actually managed to establish kind of an analogy between wireless communication and coherent optics. So I made up a little dictionary, how terms translate into each other. So wireless signals that we usually think of as packets of data, it's actually light. It can have different colors. This is a degree of freedom that we haven't used yet, but we could do it, for instance, by splitting signals according to their SSID that they transmit. So in a way, once we look at the bit pattern, signals with different bit patterns in a way correspond to different colors. And so we could have multiple emitters in a picture. We could actually tell them apart and would get a multicolored picture where every router in our room illuminates the room with a different color. This would be a very interesting thing to do in the future. It turns out that the pictures can be a lot better if you do white light holography, if you use more than one frequency band. This is something that has an analogy in the wireless domain, where increasing the bandwidth usually improves performance of radar. If you want to learn something about the environment rather than the signal itself, you usually do time domain ranging in the classical wireless domain, but in optics it's just imaging. So you form an image and you look at it. And what used to be the runtime delay of a signal is now phase and direction of a light field. So that was the work that we did. We were very happy that we made it work. We actually got it accepted in this journal, and that was kind of interesting. It's a fairly prestigious journal in our field, and so when you submit a paper, you have to fill a questionnaire on why you believe this paper is worthy of being published there. And there are categories like, you know, it's a big advance of an established technique, it's an unexpected breakthrough, it's this and that, and we decided to opt for category number 4, which is, it is of singular appeal to all physicists. So by that argument, we actually made it accepted there, and it was met with a lot of interest, not only in science, but even more so in the real world of media and of companies. And so that's what I would like to look at in the second part of my talk. What can we actually do with that? Will it ever be useful? So if you think about that question, what could you use it for? There is a very obvious answer. If you don't have it right now, then you can actually read it on Russia Today, where they picked up our story, and the headline was that this could be used to map your home. So you may wonder whether, I know some people say that this is only fake news, but I can tell you that at least for this story, this is not fake news. That's based on a real thing. So it's this idea, can we use it to spy on other people, or in a more optimistic fashion, can we use it for security enforcement and security applications? And this is something that many media jumped on. So many of the headlines that we got were related to that. Can we use that? Can my neighbor see me in my bathroom when I have my cell phone lying there? And things like that. So it's a question to which we somehow need to respond. Would that be feasible? And at least in principle, it looks like that. So if you have a Wi-Fi router in your room and you walk around, then your body will scatter some reflections, and you can pick up these reflections, run them through our algorithm, and get an image of the world. I'm somewhat skeptical whether this is a really serious use case, though, because first of all, remember what it looked like. So it's a huge device, and it's always going to remain a huge device because you need to have information on a very large area. This is what the whole scheme is based on. So even if you mounted that on a drone, you still would need to fly around many points around a building, which would probably not go unnoticed. And maybe even more importantly, it's something that actually is already being done right now. So for many of these applications, you actually don't need imaging. Imaging is kind of a bonus, but it's a complicated and expensive bonus. And you can learn a lot about the world just by looking at the signal at one point in space. And this is something that is going commercial. So there are companies that sell systems where you essentially plug something like a second router into your room. This router is not emitting signals that are used for communication. It's actually looking at signals that are scattered from the environment. It's analyzing them in a very detailed way. And by doing that, you can actually get a fairly good idea of whether there are people moving in the room, how many of them are there, are they in the bathroom or in the kitchen or whatever else. So it's something where our scheme probably is too complicated, which is good news because it's not a security concern. The bad news, if you wish, is that Wi-Fi is a very leaky thing, and this general idea that we can use the stray radiation to spy on other people, it's actually a valid security concern. Okay, if we wanted to do it, if we wanted to sell that as a security application, I think we would run into a second very important problem. And the important problem here is that if you have an application where people actually are willing to buy expensive equipment to get a lot of information, then it's going to be some kind of dedicated device. And so it's not so much more expensive to actually combine that with a dedicated, tailor-made emitter that is emitting a specific signal. And once you can do that, you can play a trick which is called ultra-wideband. And this is a very powerful trick that is spoiling the game for many of these applications for us. So I'm going to explain it in a little bit more. So the idea that you might want to use is that if you want to build something like an X-ray for rooms, you emit some signal from a dedicated emitter, you detect the reflection in a dedicated detector, you measure the runtime delay, and from that you infer whether there are people moving around and at which distance they are. So if you do that, the resolution that you get is related to the bit rate of your signal, if you wish. It's essentially the inverse of the bandwidth. So if these data packets are very broad, the resolution will drop. And from the point of view of radar, Wi-Fi actually is not a very good signal because it has a very narrow bandwidth. So for 2.4 gigahertz Wi-Fi, it's actually only 20 megahertz. And this corresponds to a resolution of 10 meters. And if you build a dedicated emitter, obviously you can drop that restriction. You can build an emitter with a much higher bit rate, and this is what people do. So you can push that up to a bit rate of gigahertz to tens of gigahertz, an emitter that is sending some garbage signal that is spread across all the frequencies up to 10 gigahertz. And by doing that, you actually get down to centimeter resolution in radar. So if you invest into a dedicated device, this is a very powerful trick to play. And this is actually being done. So there is, I did some research on the internet, and there are devices for security forces that look a bit like these devices that you use to search for pipes before drilling into the wall. You place them on a wall, it takes a few seconds, and it's going to tell you whether there are people in that room that you can't see and at which distance they are. So it gives you an image on the display which looks pretty much like that. So to sum that up, security applications, well, are an interesting thing to think about, but it's probably not a really realistic use case for this scheme. Let's look at something else. Let's look at civil engineering. I already mentioned it. There are these devices that you use to search for water pipes before making a drill. And these devices, well, they work, but I did it myself, and it's not a very reliable thing to work with. So there is room for improvement, and it's interesting to ask whether we could fill a gap in that market. So the way that would work would be that you rely on the radiation that is emitted from wireless devices in other rooms across the wall that you want to drill, and that will illuminate this wall with microwave light, so that pipes and power lines in the wall would cast a shadow, and then you would record a hologram across the wall that you want to drill, reconstruct that image, and see every single pipe. Still, we have this challenge of technical complexity, but I think in this case it would be surmountable because we could actually scale up this system from a single antenna device that is scanning the plane to a one-dimensional array of antennas, like a magic wand that you would wave across the wall, and that would give you a picture on your smartphone of what's inside. So this is a fairly realistic thing. Unfortunately, here too, you have to compete with ultra-wideband. So if you build a complicated magic wand, it's not so much more expensive to include an ultra-wideband emitter and to do very precise radar. And there are companies doing that. You may have read about Wallabout. It's a kind of a radar that you can plug on the back of your smartphone, and you can X-ray your wall, and it's going to do some signal processing and give you actually a picture of where the pipe is. So there would be strong competition. Still, our scheme would have some advantages. So we could use radiation that is actually coming from things behind the wall. That could be an advantage. And so in principle, that could be something to think about. So it could work. There's one thing that we initially thought would be a good idea. that is tracking emitters inside buildings. So this is actually a very important thing that is becoming more and more important as we move towards Internet of Things, to actually tell where in the building in three-dimensional space you have some RF tag. And our scheme in principle could do that. So we could think of installing a two-dimensional huge array of many, many antennas in the ceiling of this building, doing holography, and then see actually the position of each and every smartphone and Wi-Fi router moving around in real time. We didn't do the experiment, but we did a numerical simulation to see whether this could work. And this is what you see here. So we built a 3D model of a virtual storage hall with steel bars in the floors and with some steel shelves in one of the floor. And the image that we get is encouraging. So with that scheme, we probably would be able to track down emitters with centimeter scale precision at video rates. And what is more, we probably would even be able to get coarse information about the objects in that building. So this is a movie of the simulation data. It's essentially the hologram reconstruction as we focus onto successively lower planes, moving all the way from the top of the building to the ground floor. And so this is what we get as we move down, and we nicely see these shelves, and we nicely see these bars casting shadows in the beam before we converge on the emitter, which is appearing as a spot with a centimeter scale resolution. So this could work, but obviously it would be a very expensive thing to do. So you would need a large array of antennas. It's probably not something that you could do right away. But when we talked to companies, it turned out that there is a solution that is somewhere in between where it could get really interesting. And it's, in a way, a reduced implementation of that scheme. So rather than going to a full two-dimensional array of antennas, we could actually go to a one-dimensional array, like this magic wand. That still would speed up acquisition by a factor of 100 to 1,000 compared to our single antenna proof of principle implementation. So you could actually take pictures of large-scale, 10-meter scale structures, probably on a minute-to-hour scale, if you scanned this device around the structure by, say, a drone or a car. And once you have that data, you could actually look into the building with Wi-Fi eyes and understand how radiation propagates in there. And this could actually be relevant for this whole field of indoor tracking. So maybe to be a bit more specific on that, this is actually a very important unsolved challenge at the moment. So many companies get more and more interested in locating RF tags with centimeter scale precision to track inventories or devices. And it's a market that is actually predicted to grow to $1 billion size in a few years. However, at the present, so one very straightforward application where we could enter here is that we could do site survey for existing solutions. So if you bought some system for indoor tracking and you found that it for some reason didn't work in your factory hall, then you could come with this one-dimensional array of antennas, get this full picture, and you could see that there is actually a nasty reflection on this metallic wall, and if you replace that by some concrete coating, it will make things much better, this kind of thing. So this could be actually interesting to get the full picture only for that reason. But it could also be interesting as an R&D tool to actually understand better what these signals look like and how they propagate to make these schemes better. And there's work to do, because at the moment, these schemes are, well, very successful, but still not fully satisfactory. So people have tried many things. You can move around with a camera and scan barcodes. You can use RFIDs, but then you can only read them from a very close distance, so it's not very convenient for large-scale factories. You can use all kinds of beacons. You can tag labels with ultrasound, Bluetooth, Wi-Fi, whatever. But with that, you run into this bandwidth issue and you only get meter scale resolution. Okay. Here again, you can play the ultra-wideband trick, so you can have dedicated emitters with a very wide frequency band, and that will give you centimeter scale resolution. And this already is incredibly successful today, but it comes at a large price, and it's a physical price. These chips are expensive, so the tags will cost you something like 10 euros or more, and it's very hungry in terms of power. So you need to ship it with a battery, and you need to replace that battery every few months or years. And this is not very convenient. So there is a quest out there to make these schemes work with passive tags, where we actually, rather than having an active emitter on a label, we just have some absorbing little thing and we illuminate it by some other source and we image the shadow that it casts in the beam. At the moment, this is not doable. You, in principle, could solve that problem by many ways. You could buy more receivers, you could do more signal processing, whatever, but it's not clear which route would be the most successful. And so rather than trying them by trial and error one by one interesting idea could be to actually record this entire wavefront, look at the picture, understand how radiation propagates in typical buildings, and what part of the signal you actually need to see this shadow best. And here our scheme, I believe, could come in. We could record this full wavefront and we could simulate any kind of reduced scheme, like a scheme with only few antennas or looking at only part of the frequency band with our algorithms. So summing that up, it's an interesting technique. I don't think it's a serious security concern, but reduced implementations actually might be one. Civil engineering might be an application where we could move into. Indoor tracking probably is too difficult, but R&D for simpler indoor tracking schemes could be a very viable way to go. With that, I'm at the end. I would like to acknowledge the person that did all the work, Philip Hall. He actually was brave enough to start this project as a bachelor thesis at the time when everyone else was frowning upon the idea, and he was very successful in making all this work. So that's the end of my talk. I would like to draw your attention to the fact that you can look at wireless signal from a very different perspective. It's just light, and you can hack them by just using this stray radiation that you get. And if you do it right, you can actually take real pictures. This could be useful for maybe tracking, maybe civil engineering, probably most as an R&D tool to develop future wireless applications. So thank you very much.
We have 15 minutes for Q&A. Go.
Hello, thank you for your talk. It was really interesting. I was wondering if you could build Wi-Fi lenses.
That's a good question. So it probably would be difficult if it should be a physical lens, because so you not only would need to find the right material, which you probably could, you also would need to make it large because the wavefronts are large. But again, somewhat paradoxically, there are actually much simpler schemes to do that. So if you if you take a train somewhere in the country, you may see that nowadays these satellite receivers, they are no longer like a parabolic mirror. Sometimes they tend to be flat, like just a flat plate. And this is in a way due to a virtual lens for this radiation in that frequency band. So it's a phased array where you have many receivers and you delay the phase electronically, which is essentially what a lens does in the optical domain. And in doing that, you can simulate any kind of lens, including a parabolic reflector looking at the antenna. So for our scheme, it's actually even better. We don't need a lens because we can simulate any kind of lens in the computer. And this is something that we actually thought about doing, like building different kinds of virtual objective lenses to look at different parts of the radiation. But I think electronic solutions will probably be the easier way to go than a physical lens.
We have one question from the internet.
What is your prognosis? When can we expect a practical camera for different spectral ranges like TV or radio?
So, well, I mean, technically, I don't see an obstacle for transferring this technique to other frequency domains like radio or so. I don't think we will see it in the near future as a commercial device because applications are so limited. But maybe some lab will pick up the idea and do it. So it might be something that we might read about in a few years.
Microphone one.
Okay. Hey, thank you for the talk. Do you know how much of the technology is present in a typical router? So could a hacked router gain some physical information about its surroundings?
Yeah, this is an interesting question. So obviously you couldn't use it for our scheme because you would need to scan it. You could probably to some extent use it for these other schemes of the other groups by using this MIMO capability of scanning the beam. I don't know how technically easy it is to do that. You probably could do it in some way, but the other groups actually use development kits for routers, so it doesn't seem to be very straightforward to do at least. Or at least if you think about coming up with some project to do it, it's probably easier to buy a development kit for a router which has a somewhat more dedicated hardware than the router itself. And yeah.
Microphone 4.
Yes, the technology that you showed looks a bit like a bistatic radar system, but the power levels are much lower here. What's about the ratio between a commercial radar system and actually a ratio of power between a commercial radar system and just Wi-Fi?
Oh, I probably should be frank in saying that I don't know. So my layman take on it is that at least military radar is employing huge powers, like kilowatt maybe, and we are definitely way below that because we work with commercial devices that are in the watt range at most. So that would be a factor of 1,000, but there might be advanced radars which actually use much less power.
Microphone 3.
Hi, so how long did it take to take one of the hologram pictures, and how large is the picture?
So it took us a night. So we typically programmed the device when we left the lab, and when we came in the morning, if we were lucky, the picture was there. So it took something like seconds of acquisition time per pixel, and the pixels were something like a few hundred by a few hundred pixels in size. So that took a night, and this, of course, is a big drawback as it stands right now. But as I said, I think it would be very easy to get better in that respect. So even if we only scale it in one dimension, you take an array of antennas in one dimension, like a magic wand with many, many antennas, and you scan it only in the second one and potentially the third one, then you could speed up acquisition by a factor of 100 to 1,000. So you would be in something like minute to hour range to get a full picture of a building.
Right. Microphone 1.
So in that case, wouldn't beamforming help? Because, well, it works both ways. And this way you could also scan the signal you eliminate the space width, wouldn't that decrease the critical dimensions you need on the acquisition antenna array a bit?
Yeah, this is a very good point, and we actually thought about that. So you could come up with kind of a hybrid scheme where you do scanning to cover some space, but you take more than one antenna. Say you take a set of antennas that is like the inverse of the MIMO array in a commercial router, so it could record where the light is coming from along a whole two-dimensional set of directions. And then you might be able to actually accelerate that scheme quite a bit. And I think that if we wanted to go for passive localization and all these things, probably the solution in the end would look like that. Having a set of some enhanced antennas with a good direction sensitivity and having a discrete set of them at strategically placed points in a room, and that might be sufficient to get all the information you need to at least see the emitters.
Like having a smaller array with a lot of antennas, like 8 by 8, but this would basically end up being a phased array radar, but on steroids.
Right. So this is a very realistic thing to do, I believe. So still, if you ran holographic processing on that data, it would be a very coarse resolution image because it's only 8 by 8 pixels. But if you combine that with scanning it to only some strategic points, then that might be sufficient to actually get good pictures even without scanning a whole two-dimensional plane.
We have another question from the internet.
Aside from the paper, did you publish source code or hardware schematics to make it easier for others to reproduce your results?
We didn't publish it. Well, we wrote a very extensive supplementary material where we describe every detail of how we actually did the acquisition, including references to all the hardware components and plans. But we already got requests from hackers and students that wanted to recreate that. And of course, if people just write us an email, we will be very willing to give away all this software and information.
Microphone 3.
Yeah. Hello. You had the simulation of the antenna array in the ceiling of a building, but you said it would be too, expensive to actually refurbish a building that way. What happens if you, construct a new building and plan to build this in from the get-go? Would that be more reasonable?
Yeah. So it's probably not so much refurbishing the building, which would be so expensive. It's just the physical array of antennas itself. Unfortunately, if things grow with a square of pixels, it quickly gets very expensive. So we did some estimates of it. Even if each of these antennas would cost you only 10 cents, and you wanted to have a 1,000 by 1,000 pixel array, then you would end up with 100,000 euros of investment only for the electronics to acquire the signals. So that would be a very high barrier, I think, to a practical implementation.
Microphone 4.
Yeah, given that it's relatively easy to put a wireless PHY into continuous wave mode, do you think this would improve the signal quality, and is it something you've tried?
So setting the router to some continuous mode rather than downloading a video. We tried both, and for our scheme it doesn't matter because we throw away all this bit pattern information anyway. So we started with that, then we bought a model where we couldn't do it for some reason, and then we switched to downloading a big file. But it actually doesn't matter. For future experiments, probably one very, very powerful thing would be to move to dedicated emitters, obviously. So if we could have an ultra-wideband emitter, these pictures would look way better right from the start. And this, in a follow-up project, would definitely be a thing to do.
Hi, sorry, one quick follow-up question. Couldn't you just maybe print antennas in a cable and then just lie cables on the top of like a big warehouse or something like this?
Yeah, you might be able to find some way to make that work. But as soon as you need to at least switch the antennas to select a particular one, you end up with a switch, and that will be a semiconductor device, and that will be expensive. So I'm not an electrical engineer. I don't see a straightforward way to do it in a completely passive scheme where you only have antennas and nothing else. It might be doable, and then that array could be a viable thing to do. But as soon as you need only a little switch at every point, it's probably too expensive.
Microphone 3.
Yes. Would you think it is feasible to turn this around and use a transmitter array? Like I built a wand with 100 ESPs, which send rapidly in succession a frame and receive it with one receiver to get the hologram from there?
So to invert that, to have something like a holographic array that could create any wireless waveform that you want.
Transmitter array, like
transmitter array. Okay.
Yeah,
and then have one receiver and
yes,
and look at it. Well, yes, I think that in principle should be doable, since, as you say, it's just the inverse of our approach.
Yes.
If you could switch them one by one, probably, yeah. I think that should work. But of course, it would be way more expensive because emitters are more expensive than receivers.
I don't know.
At least in principle, I think it should be feasible.
Yeah, an ESP you get for €3. Put 100 of them on the wand, and you have one array with 100 pixels.
Right. Yeah, that's true. I mean, this is maybe in a way, this is what our colleagues did in the other schemes. So they actually had arrays of emitters, and they could phase them in a way that they could scan the beam. They looked at reflection rather than receiving the signal at one point, but this is something that you probably could do the other way too.
Okay.
Internet?
To modify your setup for different Wi-Fi standards like IEEE 802.11ac or N or any of the others?
No, we wouldn't. And we actually did these experiments both with 2.4 gigahertz Wi-Fi and 5 gigahertz Wi-Fi. The 5 gigahertz Wi-Fi looks a bit nicer in the resulting images because the wavelength is smaller, so you can see more details. But the scheme doesn't make any assumption on the standard employed, and we can transfer to any standard we like. And this is actually an interesting prospect for the future. So both the bandwidth and the frequency of these wireless communication systems is probably going to be increased in future implementations. So people talk about even moving up to 60 gigahertz or so. And with that, you would be able to see pictures of nearly optical quality, so with millimeter scale resolution. And if the bandwidth grows along with that, with much less speckles than we had, so then the whole security thing might be worth another thought too.
Could you, for example, place a small array of antennas at every corner of a building and then record different frequencies or waves which enter these arrays and calculate the position of a source in the building from the different signal strengths of different arrays receivers?
So without arrays, this is actually being done. This is how many of these indoor positioning systems work, that you measure signal strength to specific routers in the building. So we could do that, but I think that actually blowing up these antennas to antenna arrays is a very interesting thing to do. So as I said, kind of a hybrid scheme where you have some strategically placed points, but on each of them you have a small antenna array. That could be the way to go to make it a really viable scheme for commercial applications.
Still microphone 1. This is going to be the last one.
Sorry, yeah, just one quick question. What you do sounds very similar to what radio telescopes do. So did you actually talk to people from LOFAR or SKA or something like that?
Not with respect to that project. It's true. So it's very similar. They essentially do the same thing. They actually do it on a global scale. They link together telescopes on different continents to get a very sharp picture, and they think about building kilometer-scale arrays of little antennas to do that. We haven't been talking with these people yet, because they probably will be doing precisely that. So they, in a way, will use it in very much the same way, maybe in a slightly more restricted way, because they look at very focused sources and they, in a way, end up with beam scanning. But it's indeed a similar approach.
We're now with SKA moving into tomography and like 21 centimeter signals and so on, and that sounds very similar to what you were trying, and I guess they have very advanced algorithms because their signal to noise ratio is abysmal.
Right.
And so you might be actually
this is definitely a good idea. There is one important difference though, that they only look at signals that are infinitely far from the receiver. So it's a good idea, and probably we should look at that a second time. So as when we did it, it looked like looking at the coherent optics papers would be more useful once it gets to reconstructing three-dimensional things that are very close to the receiver. But they probably have they are probably very good in terms of sparse sampling and estimation schemes if you have very noisy data. So yes. Definitely.
All right. So the next talk will be here in 15 minutes. It's about machine-checked proofs in everyday software and hardware development. Please give him a hand.